Hey, welcome back, my neighbors. I'm so happy to be here today because in making this video, I learned something. And I'm so happy that you're here today because every time I make a video and I try my experiments before filming them, I now remember that you're here watching me. And so when that's happening, you guys keep me honest and at the same time I learn. So I'm very happy that you are here. So if you haven't subscribed, please like and subscribe this video and let's get into it. So in the last video, we were talking about capacitors, and in particular, we learned about capacitance and we proved that with an experiment by charging our capacitor with a direct current and watching how long it takes to charge. And we had a formula for that. You can watch it in the last video if you've missed that, and you can go back and take a look at that. But today, we're going to talk about another related aspect of the capacitor, which is its ability to let through alternating currents. Okay, and so let's talk about that. So my neighbors, what have I written here? Well, this is actually the formula that represents the reactance of a capacitor, and that is capacitors have a dynamic resistance to alternating currents, and it depends on the frequency. So Xc is actually the reactance of the capacitor. So basically it's the resistance to current flow for alternating currents for capacitors, right? So like direct currents, there's resistance, but when we're talking about capacitors with sending an alternating current through, we call it Xc here, okay? And basically what this formula says is that if we make it simple, okay, let's just simplify this one. So if we take the extremes, Xc equals 1 over, because these constants are small numbers, you can get rid of them, okay, just for the argument's sake. So you have basically 1 over Fc, okay? Well, if you like to shorten the 2 pi to something else, you can just call it C, some other constant. Let's call it K, okay, whatever that means. Now, you can see that if Fc was a really small number, let's say it was 1, okay, let's say in combination, these two equals to 1, then what do you have? Xc will be equal to 1, right? 1 ohm of resistance, right? Now, you can also see by contrast that if as Fc gets larger, Xc gets smaller, right? Because this is the denominator of the fraction. As this gets bigger, let's say KFC, I didn't actually mean it to be like that way. I don't know why it turned out to be KFC. That's rather funny. But if KFC equals to, let's say, 100, right? Then it'd be 1 over 100. Xc equals 100. You can see, and that's that's equal to 0.01. You can see that as KFC gets larger, the dynamic resistance for alternating currents gets smaller. Now also you can see that the reactance and the resistance here is also dependent on C here, which is the capacitance in farads that we talked about last time. Again, as that gets larger, as you can see, the resistance always gets smaller as well. So the rule is generally the larger the capacitance, right? Given a certain frequency given a constant frequency, and given a capacitor, the larger the capacitance, the smaller the resistance will be. Or if you have a constant sized capacitor, the increase in the frequency will decrease the resistance as well. So there is that relationship. Okay. So guys, what do I have here? this circuit that I've drawn with the capacitor and the resistor like set up like this is called a low pass filter, which basically means if you want to filter different alternating current signals and you want to only have the low frequency signals, and you don't want the higher frequency ones, this is the kind of circuit you can set up to filter that. Now, the input to this is here, generated here. This is the signal generator, and the input goes into the resistor. And the output of this filter you take from here, okay? So the way you can think of this one is, you remember the formula we just shown, xc equals 1 over 2 pi frequency times the capacitance. What that is saying is that why this reason works is because you notice that if this all works dependent on the resistance, the resistance to all alternating currents of the capacitor, okay? You can imagine as the more resistance the capacitor has, the less likely the alternating current will travel down this path and will travel to the output path, right? And the higher the frequency, or making the resistance lower, the more likely that alternating current will fall down this hole into this trap, right? So is directly related to the frequency. The higher the frequency, the more likely it will fall down, and the more likely the voltage will not be, the signal will not be registered on this line. And the lower the frequency, the more resistant this capacitor becomes, and more likely that the signal will float right past this little hole, right? This little trap. So what do we have here? Now, I've drawn another circuit here. You might recognize this. This is your standard voltage divider with resistance 1, resistance 2. Your input voltage goes to the top here, and your output voltage is between R1 and R2, right? If you don't know this one, you can look it up and you can see from any site how this one works. But the output voltage is determined by this formula, right? V out is equal to V in multiplied by resistance 2 divided by resistance 1 plus resistance 2. Basically, it's saying that the output voltage is a ratio between the between the resistor 1 and resistor 2. Okay, and that's simple to understand because you know that a volt, in a series circuit like this, the combined voltage drop of all the resistances have to equal to the source voltage. So when you have something in between here, the voltage has got to be in between, right? And that's what this voltage, what this formula describes. Now, when I redraw this is the low pass filter. I just simply redrew it in a way that looks very similar to this. So on this side, I simply redrew our low pass filter in the same kind of shape and format as the voltage divider. And now you can kind of understand why the low pass filter works, because we are still basically taking a ratio between the resistance 1 and resistance 2, right? As the resistance dynamically varies according to the frequency of the signal, this capacitor's resistance changes. Again, higher the frequency, the lower the resistance, right? You can work it out yourself if you plug these numbers in, that if the resistance 2, which is at the bottom here, imagine that becoming a low number. Well, if that's a low number, we know that the output voltage is going to be low as well, right? And conversely, if resistance 2 down here, resistance 2, right? We'll just draw it here so we can know. This is like R2. If this resistance 2 is a very low number, right? Then, sorry, I went the other way. If this was a high number, then you know the output voltage will be high, right? But of course, it's contained to within the peaks, the peak to peak voltage. It's not going to be any higher than this. It's always smaller. It's a divider after all. Okay. So what do I have here? Like in the last video, we're going to do a practical demo. I have a low pass filter set up here with generating an alternating current signal, and here from this part here and here you can see this is a resistor, and this is the capacitor that we're trying to create a low pass filter out. So never mind the other parts of the circuit; those are actually just to generate an alternating current. We'll talk about that one later, but this part, this resistor's blue resistor, and this capacitor forms the low pass filter, and we'll be measuring both the input and the output signal from this one. And hopefully, like the other video, we can leverage the low pass filter formula to derive what the size of the capacitance is. Now I've set up my scope for alternating current inputs, right? AC coupling mode. And the green represents the input signal. Yes, it is a rough alternating current signal. That's probably the best I can generate with my microcontroller setup, but that's not the point. The point is the green is the input signal and the yellow is the output signal after the filter, that is. So what I'm trying to show you here is that through a low pass filter, putting the at a frequency that's exactly at the cutoff point, right? I have here the frequency, you can tell here at the bottom is 25 hertz. So in this example, use 25 hertz. That's my cutoff frequency. So with that, I know two things. I know the cutoff frequency, and I know what my resistor size is. Now, let's do the math to figure out what is the capacitance and see how accurate we were. Okay. Now, just to show you here is the way I've set it up, right? Is that you can see that the yellow, the peak to peak voltage of the yellow channel, which is channel 2, is 2.6 volts, whereas the peak to peak of the green is 3.72 volts. What that means is the filter is already starting to attenuate the signal. And I know at this point it's exactly at the cutoff. There's a couple of things you need to notice. Yes, the voltage is approximately 70% of the input signal. Now there's a reason for that. And also what you notice that the yellow signal is actually shifted to the side. Now, I think you may understand why. You may have a feeling of why that is happening, but we're going to go back to the later mathematical models to show you why that is happening. Okay, and yes, and if you have a feeling that's happening because you think it takes a while for the current to actually charge the capacitor in order for the voltage to rise, you're right. There is a relationship to that, okay, and it shows in the mathematical models, right? So capacitors, like in the last video, they don't charge instantly, right? And that's why there's what we call a phase shift, and that phase shift is an exact point in there as well. So we'll get into that in the mathematical model, right? As you can see here, by substituting or rearranging the formula for the frequency cutoff is so that the capacitance is being solved. We plug in the values for the resistance and the frequency. So we got 2 pi times 49k ohms. That's how large my resistor was. Times the frequency is 25 hertz. You get capacitance 0.70 and a 13 here, which means 0.1 microfarads. Now, let's take a look at my capacitor here, okay? I'm gonna pull it out. pull it out right from this thing, okay? Now, let's check it out. I don't know if you can see it's upside down. It's a 50 volt, doesn't matter. 0.1 microfarads, right there. It's accurate. Now at this point, after seeing that, that's great, it works, right? But as, just like me, when I first did this, there should be a lot of questions coming into your mind right now. For example, how do they know this is the formula for the cutoff frequency? What does this have to do with the voltage divider? And why is it 0.7 or 70% of the input signal is in the output signal? Why is there a phase shift of 45 degrees? Why? So we'll get into that. But we have to go into the little math to go into that. All right. So that's what's coming up next. So let's tackle one thing at a time. Question is, why is the output voltage 70%? Okay. So going back to this original voltage divider idea here, right? Now the frequency cutoff is defined at the point where resistance 1 and resistance 2 are equal. In other words, we're on a capacitor setup where XC, which is R2 in this case over here, and R1 are equal. So the reactance of the capacitor and the resistance of the resistor are equal numbers. Now you could that instantly should pop into your mind. Why is the ratio not 50% then? Why is the output not 50% of the input, as it would be on a voltage divider with the direct currents and no capacitor in there? Why? I put question mark why here. So in order to describe that, it's because the reason why I put a question mark here is because I kind of fudged this one here, okay? Just for simple explanation, just for the idea to come through, right? Now, in reality, the total resistance down here, right, for a circuit like this with resistors only, R1 plus R2 is the total resistance. There's no question about that. But in an alternating current and with a capacitor in the flow somewhere, it turns out the total resistance is not R1 plus R2, nor is it R1 plus XC. In fact, because of alternating current, because there's a capacitor in there, basically how I can describe is, as you noticed, as you learn more capacitors, you know that the current is always used to charge the capacitor first. If we look at it in slow motion, and like in the last video of the charging, it slowly went up. Nonetheless, the current is flowing into the capacitor to charge it. So what we say here is that the current leads the voltage response, all right? And because of that, the total resistance, okay, is not a number you can just, not a simple scalar number you can add. It turns out that it's a value which is a vector value, okay? So not only does it have a resistance, it also has what's called a phase angle, all right? So you're not directly adding R1 and XC together, okay? So it turns out this is called the impedance of the total impedance of the circuit whenever there's a resistor and a capacitor involved, right? So the impedance is actually defined as a Z, okay, equals the square root of R1 squared plus XC squared. Now this should look familiar to you, right? Let me describe to you what this is. Now I've rewritten it just so I use the actual Z impedance calculation here. Now, I hope you realize why I drew this triangle here. You notice here that this is very similar to something that we've probably all studied before, right? This is the Pythagorean theorem, actually, right? It's saying that if you had a triangle with the three sides here, and you had r and xc as the sides, right? It's saying the square root of this is actually the length of this of the diagonal side, right? The square root of xc squared plus r squared, square root of those two, the sum of those two square rooted, is the length of this, right? Now that should tell you one thing already very quickly, that if we look back into our voltage divider formula, there is the standard voltage divider one has R plus XC, but we all know that R plus XC, now we all know that the diagonal of a triangle is always less than the sum of the two sides, right? It's always less than that because the diagonal is just a little bit more than either one of the sides, right? Now what is that exactly? Well, I'll tell you. If we set these R and XC as equal, side one, it's 1, let's say it's a length of 1, okay, magnitude of 1, then what is this? Well, that's easy to calculate. We can easily calculate that basically becomes 1 squared plus 1 squared, right? Square rooted. So that is the square root of 2, right? And the square root of 2, we plug that in, is 0.707, right? Now, on a standard voltage divider, right, if the resistances are equal, the answer to this will be 0.5, right? Like the ratio between the top here and the bottom will be 0.5. Now it is 0.7. I hope that describes the part about why we see in the sine wave there, why it is not 50%, it is 70% or 0.700 of the input signal. That is because in the voltage divider, remember we also said that XC, we're choosing XC and R squared, XC and R so that they're equal, right? That is the basis of the function of this low pass filter, okay? We want the ratio to them statically to be 50%. But as I said, it turns out in an alternating current circuit, the total resistance is not that, right? It is actually fairly much less than that. And that's why the voltage ends up being a little bit higher than 0.5, right? The 50%. That's basically what that one is, right? So here, my neighbors, is the gold, okay? So we have the voltage divider formula here, and I'm just going to substitute actual values. So 1 over the square root of 2 is 70%, right? Equals to, let's say the input voltage is 1. So we put 1 for that value, times XC over the rest of this voltage divider, right? So we simplify even more now. So then the next line, I've changed the XC squared to R squared, okay? Because XC squared is equal to that number, okay? We've chosen, in the voltage divider, we've chosen R and XC to be the same, right? So that's why they're allowed to be the same values here. Now, and then if we go further down, we simplify. Now it's, instead of R squared plus R squared, it's 2R squared. And then we can factor out the square root of 2, and we can factor the 2R square rooted into 2 separate square roots multiplied together. So essentially you have, on both sides now, you have 1 over the square root of 2, right? You have equal on this side as 2. So we multiply both sides by the square root of 2, and this is what we get. We get 1 equals XC over what's remaining is square root of r squared. Now, we know xc, we can change xc back into the original formula, which is 1 over 2 pi fc. So that gives us 1 equals 1 over 2 pi fc all over square root of r squared is r, right? Now, if we rearrange to solve for r, we get r equals 1 over 2 pi fc, right? Now, again, you know this one is accurate because xc is equal to r in this case, right? Now, if we rearrange this further, we get back to this, okay? We take the frequency and the resistance and we swap places. That becomes fc equals 1 over 2 pi rc. And that is essentially where the cutoff, the formula for the cutoff frequency comes from. This is its derivation, right? So my neighbors, all good things come to an end, right? And this good video has now come to an end. So at this point, I'd just like to recap what I hope I've tried to teach you guys is, number one, the relationship of frequency and capacitance to the impedance of the alternating current in capacitors, right? We've shown that with a higher frequency or a higher capacitance, the alternating currents can flow more easily through the capacitor. Higher the frequency or the higher capacitance. In general, the frequency, the signal will flow through it more easily. Conversely or inversely, when the frequency is low, then it's very hard for the signal to flow past the capacitor. Number two, we used the low pass filter concept to prove that the alternating current signal is passed through, right? Depending on the above relationship, right? We actually saw an input signal, and we saw through the low pass filter that according to the cutoff frequency, that the signal is passed through and also attenuated, right? So we basically used a lab experiment to show that these things are actually happening, right? It's not just mathematical. Not only that, we actually went and derived the formula for the cutoff frequency on the low pass filter. We went through how the low pass filter is really just a different way to, is really just a voltage divider. We went through why the output signal is 70% of the input signal. We went through why there is a phase difference, right, between the input and the output signal. And so after going through all these things, I hope that we understand a lot more about capacitors and a lot more about how to use them. So again, guys, if you haven't subscribed or you haven't liked this video, please give it a thumbs up and subscribe. I'm hoping to complete this mini-series going to shifting our focus from capacitors to inductors next. So I hope to see you there. Thanks, my neighbors. Have a nice day.